Hello. Today we're going to talk about motion in space and velocity and acceleration. So in the last section we learned that we have vector functions, and in this section what we learn is that if our vector function represents a position in space, then the derivative is going to represent the velocity of whatever a particle is, how fast it's going. And if we want to get the speed, that's going to be the magnitude of our velocity. So we can also find that by finding the magnitude of the derivative of our position function. And then the second derivative is going to represent the acceleration of a particle. So what we learned about taking derivatives last time is going to be applied now. Now, if we were to look at this in the opposite way, let's say that we started with an acceleration vector, and we know that it's the acceleration of a particle, then we should, in theory, be able to integrate the acceleration vector in order to come up with the velocity vector. And similarly, if we integrate the velocity vector, then that's going to give us our position vector. Okay, so we're going to do a little practice going back and forth with these. Now, in this particular problem, we're asked to find the velocity, acceleration, and speed of a particle with a given position function. And the position function is r of t is equal to a vector with components t squared, sine of t minus t cosine t, and then cosine t plus t sine t. And t is supposed to be positive here because it represents time. So if I want to get the velocity, then I need to find the derivative of the position. And so v of t, the velocity vector, will be r prime of t. So we'll very carefully take derivatives. The derivative of t squared is 2t. The derivative of sine is cosine of t. The derivative of this minus t cosine of t, I'm going to go ahead and use some parentheses here. We have a product rule. Derivative of the first is 1 times the cosine, and then plus the first t times the derivative of cosine, which is a negative sine of t. And then in our next one, the third component, the derivative of cosine will give us negative sine of t. And then plus, we have a product rule with t and sine of t. So that'll give us derivative of t is 1 times sine of t. And then plus t cosine of t. Whoops, I can barely squish that in there. Let me just move this really quick. All right, and close that off, and there's our vector. Let me just clean that up a little bit. So this leaves us with a vector with components 2t, and then in the second component I have a cosine t minus cosine t, so those go away, and then I get a double negative, so it's a positive t sine of t. In the third component, the negative sign and positive sign go away, and then I have a plus t cosine of t. And that is my velocity function. Now, if I want to find the speed, because that's the another thing that we need to find, then what I will do is I will find the magnitude of this velocity vector that I just found. So remember, magnitude is just going to be the square root of the sum of squares of the components. So I'll put 2t in and square it, t sine of t in, getting squared, and t cosine of t will get squared. Working this out, we have the square root of 4t squared plus t squared sine squared of t plus t squared cosine squared of t. And this finally simplifies to be, it looks like if we factor out a t squared, we leave behind a sine squared plus cosine squared, which is 1. So overall, we have square root of 5t squared, or in other words, square root of 5 times t. All right, last but not least, the acceleration. Acceleration, that'll be a of t. That's going to be the derivative of velocity, or in other words, the second derivative of the position function. So we go back up to the velocity function. The first component was 2t. The derivative there will be 2. The second component was t sine of t. The derivative will be sine of t minus plus t cosine of t. The third component was t cosine of t, so the derivative will be cosine of t minus t sine of t. And that's it. We have velocity, speed, and acceleration. Now, in the next position, or in the next problem, we're given an acceleration vector. We know its components, and we're supposed to find the velocity and position vectors. And we are also given an initial velocity and an initial position. I'm going to write all of these again just using the angle bracket notation because it's just more comfortable for me. So my acceleration has components sine of t, 2 cosine of t, and 6t. My initial velocity has components 0, 0, and minus 1. And my initial position has components 0, 1, and negative 4. All right. So the very first thing, I want to find my velocity. Velocity is going to equal the integral of the acceleration vector. So we're looking at the integral with this vector, sine of t, 2 cosine of t, 6t, dt. And when I integrate this, what's going to happen, remember that the integral is going to affect all three components inside. And so I'm going to get, in my first component, the antiderivative of sine is negative cosine of t, but this is an indefinite integral, so I need a constant of integration. I'll call it plus c1. In my second component, I have 2 cosine t. The antiderivative is 2 sine of t plus c2. And then the 6t, the antiderivative of that will be 3t squared plus c3. Okay, so here's where we're going to use the initial velocity. We're told up here that the initial velocity is a vector with components 0, 0, and negative 1. So if I plug in 0, I should be getting 0, 0, and negative 1. So I'm going to plug that into my actual velocity function. Negative cosine of 0 is going to be negative 1 plus the c1. Sine of 0 is 0, so I get 0 plus c2. 3 times 0 squared is going to be 0 plus the c3. So what this means is that if I equate components, I have c1 minus 1 is equal to 0, so c1 is equal to 1. It looks like I have c2 is equal to 0, and I have c3 is equal to minus 1. So now my final velocity vector has components 1 minus cosine of t, and then 2 sine of t, and then 3t squared minus 1. All right, now I need to find my position vector. So my position vector I cannot find until I have my velocity vector and all of the constants of integration figured out. So I have that. Now I can say my position vector is going to be the integral of the velocity vector I just found. So I'm going to go ahead and plop that in there. We have 1 minus cosine of t, 2 sine of t, and 3t squared minus 1 dt. Finding antiderivatives, in the first component, I get t, I get minus sine of t, and I need another constant of integration. So I'm going to switch to plus d1. In the second component, the antiderivative of 2 sine of t will be negative 2 cosine of t plus d2. In the third component, I get t cubed minus t plus d3. Okay. Now I have my initial velocity up above. It says my initial velocity, when we plug in t as 0, we're going to get a vector that has components 0, 1, negative 4. So let's use that. R of 0 should be giving us 0, 1, negative 4. So I'll go ahead and plug in 0. In my first component, 0 minus sine of 0 is 0, so all I have is the d1. In my second component, negative 2 times cosine of 0 is going to be negative 2 plus the d2. Third component, I have 0 cubed minus 0 plus d3. I put that all together and I get d1 is equal to 0. d2 minus 2 is equal to 1. And d3 is equal to minus 4. d2 will be, sorry, I accidentally wrote d3. d2 will be equal to 3 when I solve for it. Okay, so now I can put those in, and I have my final position vector. R of t is equal to a vector with components t minus sine of t. d1 was 0, so nothing there. And then d2 was 3, so I'll rewrite this as 3 minus 2 cosine of t. d3 is equal to negative 4. I accidentally didn't put my equal sign there. So we're going to get t cubed minus t minus 4 for that component. So here is my position vector. Here is my velocity vector. Just to be sure that's all they wanted. Yep, velocity and position. That's it. Okay, so that's how you're going to work with your derivatives and your antiderivatives to come up with acceleration, velocity, and or position vectors. Now, we also have projectile motion. Projectile motion is when you are, shooting something up into the air. What goes up must come down. And then there's a couple of other things that are very true about that with projectile motion problems. Typically, the force that's acting on an object is only going to be the force that's due to gravity. And so we get this first equation right here. Force is equal to mass times acceleration. But what that implies for us is a very important thing, is that the acceleration vector in a projectile motion problem will typically be a vector that has a 0 horizontal component and negative g, 9.8 meters per second squared, or if we're using other units, then we'd do the 32.2 feet per second squared. So in your book, they kind of walk through, like, how do we come up with velocity once we know what our acceleration vector is. But I don't think it's good to try to memorize this stuff because we can just go ahead and find an antiderivative. So what I'm showing here in this next step is I find my velocity vector by integrating my acceleration vector, the 0 minus g, and I get my constants of integration right there. And then we're going to have some initial velocity, or we'll know an initial speed, right? And if we have an initial speed, that's one thing that could come up. Let's see, where do I want to put this? So we have this right here for an initial velocity, but if given an initial speed, so that would be the magnitude of the velocity, then the initial velocity would be this initial speed times a vector with components cosine of theta, sine of theta. So it's just using the same rules that we were using before to come up with a vector using a component form that has cosines and sines when we only know the magnitude, okay? So that may happen to us. Once we have figured out what our constants of integration are for our velocity vector, we'll be able to find our position vector by integrating velocity. And here I've shown it where C1 and C2 still are not known, and what happens is we'll integrate those and we'll end up with T's with those, and we'll have a new constant of integration, the D1 and D2. And so this is our overall format for coming up with our position vector. Now, let's see. We would have our initial position given to us, and we don't usually have to worry about there just being like a magnitude of position. Typically, we know what our position is, and then we can go ahead and put this all in here. Now, if we were to summarize this, and you like to memorize things, then the velocity vector is always going to be of this form. It's going to be minus g, where g is the acceleration due to gravity, minus gt j hat, plus whatever your initial velocity is. And then the position vector will always be minus 1/2 gt squared j hat, plus a t times the initial velocity, plus your initial position. So let's see, from here, what do we want to go to? Let's see. All right, so I talk about here where we get sometimes the initial velocity can be written in terms of these sines and cosines. So I already talked about that, but I do have it here. And then that would make the form of our initial position function look just a little bit different. So here's what's happening. We would have some starting point for our projectile, and it would maybe shoot off at some angle. And that angle is the angle created with the ground. And so that would have some value, alpha, since I'm using alpha right here. Now let's say we've got our initial velocity when the projectile shot off, and then after that, the only thing acting on it is the force due to gravity, and it'll land somewhere. So we'd want to know some questions like, where does the max height occur? And that's going to be when the vertical component of velocity is 0. So there'll be like just this quick moment up here at the top, right? If this is our position function, at the top it has a 0 tangent, which means that the velocity vector has a 0 component in the velocity. For your vertical component. Another question that might come up is, where does the object land? And this will be when the vertical component of position is 0. So you'll be asked these sorts of questions, and you have to kind of decide, do I need my position function to help me answer this, or do I need my velocity function to help me answer this? So let's go ahead and work through an example. And here we have a projectile. It's fired from a tank with an initial speed of 400 meters per second. And we want to find two angles of elevation that can be used to hit a target 3,000 meters away. So here's what we've got. We've got a projectile that gets shot off, and it's shot off with an initial speed. So that's going to be the magnitude is equal to 400 meters per second. Here's the ground. This is going to be shot off, and then we want it to land 3,000 meters away. Okay. We need two different angles of elevation that can be used to hit this target. Our angle of elevation is the angle that is created between the ground and the projectile when it's shot off. And so here's our picture of what's going on. We should start off stating what we know. So what's known here is the initial velocity. The initial velocity, we'll have to create the vector because it wasn't given to us, but we do have the initial speed. So we know that the initial velocity will be the speed times cosine of the angle in the first component, and the speed, 400 again, times sine of the angle in the second component. We also know that the acceleration due to gravity is going to equal 0, negative 9.8, okay? And then the initial position, since this is fired from a tank, we'll assume that the initial position is right at the origin. The only time we would not assume that it's at the origin is if the tank was maybe elevated off of the ground. They didn't give us a height for elevation, so the best we can do is assume 0, 0. All right, so now let's see what we can do. We know acceleration, and that's kind of the only thing we really have to work with other than our initial conditions. So maybe we should start with the acceleration and work backwards and come up with a velocity vector and a position vector. So velocity vector, again, is going to be the integral of the acceleration vector, dt, which will be the integral of the vector 0 with negative 9.8 dt. When I integrate this, I get a vector with components 0 plus c1 and negative 9.8t plus c2. Okay. Now, I know that the initial velocity was given to me as being 400 cosine of theta and 400 sine of theta. And this is supposed to equal my velocity vector that I just found evaluated at 0, which would be c1 and c2. So it looks like equating coefficients c1 is equal to 400 cosine theta and c2 is equal to 400 sine theta. We have an exact equality. So our velocity vector has components 400 cosine of theta and 400 sine of theta minus 9.8t. Okay, I know we don't know what theta is, but that's something that we're trying to find by using the information that they've given us. See if we can get there. So still at this point, I can't do much, but maybe I could keep going and find my position vector. So I'll do that. My position vector, r of t, will be equal to the integral of the velocity vector I just found. So I'm going to plug in my velocity vector. Components are 400 cosine of theta, and the second component, 400 sine of theta, minus 9.8 t dt. Now remember, we are integrating with respect to t, so theta is not a variable, it is a constant. So when we integrate, in the first component, we get 400 t cosine of theta. In the second component, we get 400 t sine of theta minus 4.9 t squared. Whoops, I forgot something. Hang on. I need to go back in and put in plus d1. Never want to forget your constants of integration. And so in the second component, I have a plus d2. All right, now I can apply my initial conditions for position. They tell me r of 0 is equal to 0, 0. And so that means I should be able to plug in 0 for t in my vector I just found. Plugging in t in the first component leaves just d1. In the second component, if I plug in t, I just get d2, which means I have kind of a direct equality here. d1 is 0 and d2 is 0. So my final position vector, r of t, is just 400 t cosine of theta and 400 t sine of theta minus 4.9 t squared. Okay, now what we're trying to figure out is the angles that would allow the object to hit the ground at 3,000 meters away. So we need to find theta when the object moves 3,000 meters horizontally and 0 meters vertically. So in other words, we want the position, so that is the position r of We're not sure when this time will happen, but we want to know when r is equal to 3,000 and then 0. Okay? So we're taking our vector function, r of t, just taking the 400t cosine of theta and the 400t sine of theta minus 4.9t squared, and we're setting this equal to 3,000 and 0. And so we're going to equate coefficients and see if we can come up with a system of equations that we can solve. Equating the first coefficients gives us 400t cosine of theta is equal to 3,000. Equating the second components gives me 400t sine of theta minus 4.9t squared is equal to 0. Okay, now I'm noticing that in the second equation I have a quadratic, and remember we're solving for t. Eventually we want to solve for theta, but it would be nice if I could solve for t right now and just see what that gives me. Maybe I get a couple of t values and I can use those to solve for theta. So in the second equation, I can isolate and solve for t. So it looks like I can factor out a t. That leaves behind a 400 sine of theta minus 4.9t. That's all equal to 0. So the zero product property tells me that t is equal to 0, which that's going to be when the projectile's first shot off, or t is equal to 400 sine of theta over 4.9. This second time is when the projectile lands. The first time is when it leaves the ground. Or I should say the tank. Okay, so using this, I'm now going to substitute this t value, t equals 400 sine of theta over 4.9 into equation 1. And I'm also going to add an extra sheet of paper because I'm running out. Okay, so if I sub this value for t into equation 1, what I get is 400 times 400 sine of theta over 4.9 times cosine of theta is equal to 3,000. Okay, now I'm going to keep my sine and cosine on the left-hand side and move everything else over. So I get sine of theta, cosine of theta is equal to 4.9 times 3,000 over, it looks like 160,000, a big number. Okay, now if I plug this value into my calculator, so I'm going to kind of need those, working this in real time here with you, 4.9 times 3,000 divided by this 160,000, this is going to give me 0.091875. Okay, now on the left-hand side, unfortunately, I have sine and cosine, and I can't use any sort of zero product property when I have two things on the left and a number on the right. So I need to use a trig identity. Sine theta cosine theta is equal to 1/2 sine of 2 theta. So I can use that in order to solve for theta now. So first I'm going to isolate sine of 2 theta, move on to the next page as well. Sine of 2 theta will be equal to twice the 0.091875, which means 2 theta will be sine inverse of whatever this result is. We'll multiply by 2. That's going to be 0.18375. Okay? And let's see, that means that theta is, well, let's actually figure out what sine inverse of that is. So sine inverse of this answer is going to be, so 2 theta is equal to about 10.59 degrees, or we want to get the other side. 2 theta is equal to 180 degrees minus 10.59 degrees. Okay, so 180 minus 10.59, it's going to be 169.41. Okay, so on the left-hand side, theta is going to be 10.59 divided by 2 is 5.295, or about 5.3 degrees. I'll just write the 5.295 degrees, or theta is going to equal 169.14 divided by 2. That's going to be 84.57 degrees. And so those are the two possible values that would give us a landing that's 3,000 meters away. So the idea with the first one at 5 degrees is that you shoot low, very low, and the projectile never goes very high and lands 3,000 meters away, or you shoot high and the projectile goes up and comes down at the same spot. Okay, so hopefully this allows you to have a little bit more comfort level with coming up with the velocity and the position functions when you only know about the projectile motion and the acceleration due to gravity. If you do have any questions on your homework about this, please reach out.